Courses in the cement industry. Present to you. In this course we will explain Pyro process equipment. Pyrofloor cooler. KHD has developed Pyrofloor cooler, a new clinker cooler, which has already received much recognition in the cement industry. The new cooler combines the best solutions that the development has found for each of the two fundamental, mutually interacting functions a clinker cooler has to accomplish. Clinker conveying based on the walking floor principle. Aeration controlled by self-regulating valves. The design process was based on the following requirement specification, with their respective solutions. Cooling of clinker principles. Any clinker coolers, thus have a many function. 1. To transport the clinker away from the rotary kiln. 2. To cool the clinker for subsequent safe handling. 3. To preheat the secondary and tertiary combustion air. 4. Maintain C3S in an integrated manner, and not returning again to C2S. Advantage for Pyrofloor cooler. 1. High recuperation degree. 2. Active clinker distribution. 3. Self-regulating aeration. 4. Low cooling air amount. 5. Low clinker outlet temperature. 6. Low wear and maintenance. 7. Low construction height. Design and functioning for Pyrofloor cooler. 1. Clinker is produced in the pyro section of the cement plant, comprising of raw meal preheater, rotary kiln, and the clinker cooler. 2. The process works on the counter current principle. Raw meal is fed into the preheater, burnt in the rotary kiln to produce clinker at almost 1400 degrees, which is then cooled down in the clinker cooler. 3. Air at ambient temperature enters the cooler, by means of aeration fans, is heated when passing through the hot clinker bed, in the process cooling the clinker. 4. To reduce the fuel requirement of the rotary kiln system, part of this air is directed into the rotary kiln. 5. The residual cooling air portion passes through the clinker, is withdrawn at the outlet, dedusted in an electrostatic precipitator, and directed into ambient via a stack. See this video about Pyrofloor cooler.
The highlights of KHD Humboldt VDOG's Pyro equipment are well known all over the world. The Cyclone preheater is best known under the name Humboldt preheater. But KHD has also pioneered in highly advanced calciners for increased efficiency and secondary fuel utilization, rotary kilns, most advanced clinker coolers, and burners. In this film, the latest design of KHD, the Pyrofloor clinker cooler, is presented. The Pyrofloor clinker cooler features a revolutionary new concept with extremely reduced maintenance costs, self-regulating aeration, and no more clinker riddlings. Completely new solutions and major improvements of existing concepts were found in order to introduce a fresh new approach to clinker cooling. The highlights of the Pyrofloor clinker cooler are a highly modular design, the conveying system based on the walking floor principle, a new aeration concept, and new sealing concepts. The mechanical design of the Pyrofloor clinker cooler is based on strictly modular components. This approach ensures easy adaptation of client-specific needs and requirements. Moreover, assembling and installing the cooler is possible in a very straightforward way. This helps to keep down costs and enables for easy upgrading. Clinker conveying is based on the well-known walking floor principle, which has proven its reliability in numerous bulk conveying applications. The principal embodiment consists of several lanes, arranged beside each other alongside the direction of clinker transport. These lanes are pushed forward simultaneously and retracted in such a pattern that no adjacent lanes are moved at the same time. Thus, the transmission of the impulse into the clinker layer during retracting is tearing off, and the clinker bed behaves like a solid body, which is held in place by the majority of the non-moving lanes. A permanent cold clinker cushion provides autogenous wear protection by preventing contact between the hot-moving clinker and the metal parts of the cooler. The Pyrofloor clinker cooler features a completely new developed aeration concept to avoid the typical problems like hot spots and air fountaining, which occur in more conventional designs. Flow regulators with different rated flows are placed beneath the grate in order to provide a well-tuned aeration. By combining the flow regulators to each one aeration cassette, the basic problem of clinker cooling is solved. The non-uniform height and temperature distribution of the clinker bed can now be met with a precisely balanced air supply to any spot of the grate without the usual complicated ductwork and flaps. The aeration sections created in the Pyrofloor cooler are small enough to keep up their controlled aeration even if a neighboring section should be subject to temporary failure. In case of temporary defects in the clinker layer, the integrated self-regulation mechanism guarantees a constant airflow and thus prevents blow-throughs and hotspots. As this regulation happens only locally within a very small area, the rest of the bed won't be affected. The Pyrofloor clinker cooler utilizes newly designed unique contact seals for all those places where air could otherwise stray through labyrinth gaps. By this technology, neither air nor clinker can find its way through gaps where it should not pass. Due to the contact seals and due to the fact that there are no elements passing through the grate surface, there is no possibility for clinker fines to fall down below the aeration surface. Hence, any spillage provisions like hoppers and drainage are no longer necessary. At the same time, the height required is significantly reduced in favor of the height level of the complete kiln line. From the beginning of the design phase to the first installation, it was the outstanding ambition of the specialist at KHD to find new solutions for all of the requirements of a clinker cooler. The result is nothing less than a truly new concept and realization of a clinker.
Instrumentation and automation in Pyrofloor cooler. 1. Field instrumentation. 2. Cooler hydraulic PLC control panel, HYDROC PLC panel. 3. Process control system, plant DCS. 4. Pyrofloor cooler controller, Pyrofloor clinker cooler expert system, for cooler control and optimization. Field instrumentation in Pyrofloor cooler. 1. Radar type level sensors. These sensors render measurement of clinker bed level, on lanes inside the cooler. One radar sensor is installed per lane. Sensor heads are fastened to the antenna extension, through a flange connection at one end. Flanged at the other end is a conical horn, which protrudes into the housing ceiling. Cooling air, via blower, is provided for sensor head. Purging, via compressed air, is provided for protection of horn antenna. 2. Temperature and pressure measurement. A thermocouple is installed underneath the cassette, for each lane. Temperature signal from thermocouple is wired to plant DCS via a temperature transmitter, 4 to 20 mA, or Profibus PA type. One set of thermocouple, and temperature is used per lane. Pressure sensors are mounted, at predefined points underneath the cassettes in different rows. In this way pressure underneath the clinker bed can be determined. Pressure signal is connected to plant DCS via a pressure transmitter, 4 to 20 mA, or Profibus PA type. Pressure is measured at 2 points per lane. Cooler hydraulic PLC control panel, HYDUC PLC in, Pyrofloor cooler. 1. Movement of cooler lanes is rendered by a dedicated hydraulic system. This is envisaged as a sub-control system governed by dedicated Siemens PLC. 2. Cooler hydraulic PLC controls all operational aspects of cooler hydraulics. It is linked to controller for the cooler section of plant DCS system via Profibus Delta P. 3. Hydraulic PLC starts or stops hydraulic pumps on receipt of relevant requests from DCS. 4. The lane movement is started on receipt of relevant request from DCS. Set points for CPM, stroke length, and lane to group assignment is sent to hydraulic PLC from Pyrofloor clinker cooler via plant DCS. Sub-control system for cooler hydraulics in Pyrofloor cooler. Process control system plant DCS in Pyrofloor cooler. 1. Facilitates supervisory control of Pyrofloor cooler. 2. Cooler under grate pressure, temperature, and bed level signals from radars are directly connected to plant DCS. These signals are passed on to Pyrofloor clinker cooler for further processing. 3. Directly controls pyro crusher operations. Logic and interlocks for pyro crusher are programmed in DCS. 4. Directly controls aeration fans. PID loops and interlocks for cooler fans programmed in DCS. However, in auto mode of aeration controller, flow set points are sent to DCS from Pyrofloor clinker cooler. 5. Acts as bridge for data and signal exchange between Pyrofloor clinker cooler and HYDUC PLC. See this diagram about process control system plant DCS in Pyrofloor cooler. This diagram about Pyrofloor control system architecture. This diagram about process control system, visualization of Pyrofloor clinker cooler. Pyrofloor clinker cooler transport controller. Transport controller has two modes, manual and auto. Manual operation. 1. Operator assigns all lane into 3 groups, in a way that no adjoining lane are assigned to same group. 2. Operator enters set points for cycles per minutes, common for all lanes. 3. Operator enters stroke length for each lane in millimeter, this can also be set individually for each lane. 4. Based on these operator inputs, Pyrofloor clinker cooler calculates forward RET velocities, forward RET time and sends these calculated parameters to HYDUC PLC via plant DCS. 5. HYDUC PLC then operated the cooler lanes at speed, stroke based on these parameters. Auto operations. In this mode 2 controllers can be implemented, viz. Restricted controller and standard controller. A. Restricted controller. 1. Operator gives the set point of bed level, and restricts common stroke length for all lanes, to a fixed value. 2. Bed level signals from radar sensors are processed at Pyrofloor Clinker cooler, to determine mean level inside the cooler. 3. Controller algorithm evaluates the deviation of average level against the set point, and controls lane speed by varying cycles per minute. Standard controller. 1. Operator gives the set point of bed level, and sets the minimum and maximum values for stroke length. 2. In this mode, one controller is assigned to each lane. Bed level measured on each lane is fed to the response controller as process input. 3. The controller outputs average transport velocity requirement based on the deviation of actual level measured on the lane from its response set point. 4. This requirement is then fed to an optimizer, which evaluates this and generates outputs for forward stroke time, RET stroke time, stroke length for each lane, and CPM output common for all lanes. Operation Guide. Transport. 1. Transport by walking floor principle. 2. Forward, all lanes together. 3. Backwards, individual movement of lanes, and group of lanes. 4. Bed height measured by radar system, 1 radar for each lane. Best bed height, 800 to 1000 mm as an average. 5. Transport efficiency is a function of clinker granulometry and aeration. Clinker granules 5 to 25 mm are preferred. 6. Parameters, CPMS, stroke length, operation mode. 7. CPM, 1 to 10. 8. Stroke length, 80 to 350 mm. 9. Operation mode. It is divided into manual, restricted controller and standard controller. Aeration. 1. Chamber number 1. Always high airflow, to avoid snowman formation. 2. High cooling efficiency, due to big temperature difference clinker and air. 3. Minimize disturbance of clinker bed. 4. Chamber number 2 and 3, small coolers. Chamber number 2 and 4, medium coolers. Chamber number 3 and 5, big coolers. Aeration. The new flow regulator. One of the most important features. 1. Converts chamber aeration into direct aeration, on the whole grate without the usual ductwork and pressure loss. 2. Doses just the right amount of air to its locality. 3. Reacts on changes within the clinker layer loading, by itself and keeps the airflow constant. 4. Increases heat transfer. 5. Requires no automation. 6. Unique patented design allows operation in movable systems. Improved aeration. 1. Optimal aeration due flow regulators, and aeration cassettes. 2. Optimized response on local conditions. 3. Prevention of locally bad aeration. Clinker aeration. Objective. Maximizing heat transfer. Heterogeneous, Non-stationary fields on the grate. 1. Bed height. 2. Temperature. 3. Granularity. Local supply of cooling air matching to the energy level, at any spot of the grate. 1. Highest heat transfer. 2. Low blow-through tendency. 3. Low Red River tendency. See this video about from the site. The new flow regulator. New sealing solutions. Optimized contact seals. On of the most important specifications. 1. No spillage. 2. Self-adjustment. 3. Highly wear resistance. And therefore low height. 1. No hoppers and spillage handling equipment. 2. No fall-through design. See this video from site. How installation new sealing. Static inlet seal. Triple safety against spillage. 1. Autogenous clinker sealing. 2. Spring-loaded contact seal. 3. Pressurized air rinsing. Easy to maintain. 1. All parts accessible from above the grate line. 2. Cassette type. Hydraulic drive. 1. Active pump redundancy. 2 pumps in permanent parallel action. 2. All lanes driven, and controlled individually. 3. All lanes driven by 2 cylinders, always pull never push. 1. Self-stabilization of lanes. 2. Sturdy single-action cylinders, phi rod, and phi cylinder. 4. Full operability is granted, without any functional loss even if one pump trips. See this video from site, about hydraulic drive. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.